Well, here we are, yet another LED bulb teardown. I picked these up at Costco recently. They're Conserv Energy branded LED high power 60 watt replacement. It's interesting that I've seen, like, Costco literally had two 75 watt replacement bulbs, for can lights, effectively spotlights, one of which was 13 watts and one of which was 18 watts. So I don't know how they're doing their math, but apparently two different wattage bulbs are equivalent to one other variety of bulbs. I think they're kind of talking out their posterior a little bit, and or just making shit up. Picked these up. They were actually the same price as the previous bulb I tore down, $13, $14. I actually like the light produced by these a lot better. They're much more, they're warmer, and it's also significantly brighter. So I'm actually fairly in favor of, I think I'll probably purchase these in the future. Anyways, I bought two, one of which is currently being used, and then also this one, which I actually bought this bulb just to take apart. They're very hefty. It's definitely a solid bulb. One of the things of interest you can see is that they make a big deal about it being omnidirectional, and from the look of it, it actually has like a ring of LEDs, and then there's actually a solid white baffle, and then there's a couple that point out towards the end. Fate Electric Conserv Energy. Of course horribly misspelled, to try and be, cool or whatever. The marketing, nut jobs who tend to think that, writing C-O-N-S-E-R-V rather than C-O-N-S-E-R-V-E somehow makes them hip or something. I don't understand. Anyways, you can probably tell from the sound of it that plastic on these is it's plastic rather than glass like the previous ones. Also of interest is the fact that it looks like they're using the same half watt. I think somebody in the comments said these were one of the Luxion Rebel types. So this may in fact be, considering the package and some of the layout, this may be the same manufacturer, just rebranded by different companies. It doesn't say ECS on here or anything like that like it did on the other one, so I'm not too sure. Anyways, so you can actually see it looks like there's only one PC board in here. There's a couple that point up, and then if you look down there, there's a ring, and then they're using this white plastic as a reflector to give them the light output out the sides. Effectively a very bright white surface is actually a very efficient reflector. You can actually get better efficiency than a mirror, but it's not a like a optically perfect mirror. So mirrors of course still have their applications, but in lighting it turns out like a flat white surface is a better, more efficient reflector than aluminized or other sort of surface. Wow, look at that. So this is 13 watts and it claims 13.5 watts, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 36. So there's 36 there. So that's so they're underdriving these. Remember, the previous bulb I took apart used 10 of them, or no, it used 16 of them for 8 watts, and this one uses 36 for 13 watts. So I would imagine they're running the LEDs a lot less hard in this bulb than they were in the previous LED bulb, which may mean that the life expectancy of this bulb is presumably significantly better, which is another thing about it that I approve of. You can see this is typical metal core PCB, and actually if you look at the reflectivity, you can see that it looks like they, rather than just run traces, it looks like they basically just cut out to make all the separate lands effectively electrically isolated, which is a very good thing to do, because that means that effectively these two LEDs are thermally conducted to this whole pad, and therefore the thermal resistance between that pad and the aluminum core is much less than just the thermal conductance between the LED. So by increasing the area of the copper, you effectively increase the thermal you decrease the thermal impedance between the copper, the LEDs and the aluminum core. So that effectively increases the efficiency with which it heat sinks. So that means that whoever designed the circuit board wasn't totally, off their nut, like a lot of the stuff coming out of China seems to be. So fortunately, the plastic has a lot less silicone on this one from the look of it, which is something I can only approve of. It actually looks like that it would be possible to remove the cover plate on this and give you a directional light with very little effort. Again, it was just held in with a little bit of glue, and there are 4 tabs on here. So as usual, we have a metal core PCB. This one's held on by 3 screws. I'm just going to cut the wires. Once again, these wires this is solid core, it's not stranded wire. I don't see that being that much of a problem, but you know, it's interesting. Actually, yeah, it's solid. So let me just remove the LEDs. So another thing of note is that these are not held on by silicone. So it's marked Scholar, so I wonder if that's one of the companies behind this. Also, 26th of October 2011. So this is a fairly recent, well, it's a year. Literally almost, it's actually almost exactly a year old. So, I mean, you can obviously tell, I bet there's very rapid turnaround on LED anything. So, stick the spudger into there, and oh, that's intriguing. So there is basically no heatsink goo. I mean, there's a couple little dabs, but I guess they have so much contact area, and the efficiency of this heatsink is going to be mediocre at best. I mean, you don't have a lot of surface area. One thing of interest is that on these bulbs, you know, assuming they're used in like a table lamp, you'll actually get airflow through the fins because these holes are open. So it will probably be a slightly more efficient heatsink than the previous bulb, where they effectively blocked these off, and therefore the heatsink was kind of silly. Also of note is you can see that they actually have separate screws. On the previous bulb, when I removed the circuit board, the center of the bulb just fell out. On these, it appears that it's held in by a separate set of screws. Let's take these out, and I would guess it's potted because all of these things seem to be potted. Though I guess we'll see how right I am about that in just a second. So removing those 2 screws, and I'm betting it will then pop apart. Yes. So it's just a very snug fit. Okay. Up. There we go. So there is the actual driver. And yeah, it's potted in exactly the same type of crap as the last one, for the look of it. So here are your 2 leads coming off. And just a solid goop. So here's kind of the metal can. It's interesting that they have like a cover on this one. Presumably that's just for this, which is just to prevent the wires from rubbing against this hole. Which looks like it may have been punched after the fact. I can't really make it out. I'm not sure if that's part of the original machining. Definitely the holes were machined after the fact. But this again, some sort of presumably die cast or something. You know, it might be aluminium, I don't really know. So here is the ballast. Where is my little plastic cell? There it is. So if you need to take stuff like this apart, it's a X-Acto brand. X-Acto brand. It's actually a backed saw. So it's actually a very fine saw blade, and they just sell them at hobby shops. And it was what I used to take the previous one apart after like way too much fucking around trying to do it in a different method. It seems to be the most efficacious solution. What I'm going to do is what I did last time, which is try and pop the bead off. So go. So there's the end cap bead. This is glass. So if I could get like a wedge under here, you can see they've basically just dimpled it inwards, and that's what's effectively holding this on. Why I can't move it. Actually, the last one kind of screwed on. Oh, well, have a look at that. So you can see that they actually cast these threads into the plastic, and then the whole thing kind of screws on, and actually you can see that here's one of the contacts, and it looks like they filled this up with potting compound, so this whole thing just tore off. And made a mess once again. This is probably going to be about as messy as the previous one. So I'm going to have less glass shards because I didn't break the little glass pip on the bottom. So, there we have the two power leads, hot and neutral. Neutral's stranded, and they just laid it in a section over there and just kind of threaded the thing onto it and then assumed it would make contact. Sorry, I'm leaning my head in front of the camera again. Yeah, this was much longer than the other one. Mostly through. Wow, look at that. You can actually see light through the crack. Alright, just a little bit further, and then I will start with the probe. Let's try and go sideways a little bit. So now let's just stick a screwdriver in there. Yeah, I have to cut a little further. Alright. Ah. Cool. So that kind of just detaches the potting compound. Let me cut it on the other side. It's definitely peeling open. like most of these things, you have to take one apart to figure out how to take more of them apart. And then once you've figured out the tricks to it, it's so much easier later on. But first one's the hardest. Because I took that first one apart, now I can get into these ones without really any significant trouble at all. Yeah, just catching all the wires. Yeah. Oop. Would really amuse me if this was the same board. I guess I'll see in a second. Just a little bit of assistance. Nibble away at the threaded section. Okay, so that is one side, so there we are. Now I just need to take a spudger and kind of just shazam. So there is the interior of the driver. One mess later. Now let's try peeling away some of the potting compound. So you can see the transformers in there. There's one little section of it. So, oh yeah. Yep. Actually, that's not a part of the transformer. That's a cap. Fortunately, it's the same kind of chunky potting compound. That just kind of falls apart if you look at it funny. It doesn't seem to adhere much to anything but itself. It's kind of okay. There's a power transistor in a funky little package. Okay. So these are presumably the output capacitors. They are Sam Young branded. They are 105 degrees Celsius though, which is nice. So they're not totally cheap. Actually, I don't know where the power transistor transformer is. This one may not be isolated. Oh, nice, look at that. So this does in fact appear to be an unisolated one, as opposed to the previous one which I took apart, which was. So I guess they're relying on whatever isolation they get in the metal core PCB. So this is presumably line connected, which is kind of how I would have expected these things to work. I mean, even if that's an opto, that's not a lot of creepage there. Oh yeah. Let's keep peeling off this goop. There's more. Oh, this is the transformer. I thought it was. But it's much smaller. That's interesting. It's very compact. Also, where's the isolation barrier? So we kind of want to come up. Alright. So there is the input fuse. 1 amp, 250 volts. Oops. Oopsie daisy. So here we're kind of starting to get through to the transformer now. All the componentry around it in any event. Oops. So there's the main capacitor. So there we have it, 400 volts, 2.2 microfarads. So that's actually a bridge rectifier. So this is indeed non-isolated, as far as I can tell, because that's a bridge rectifier. And you can see that, you know, here's one of the output pins, and you follow that trace. So one of your outputs runs to that diode, which runs right to the rectifier. So the output of this is not electrically isolated from the input. So this one is not, in fact, you can't touch. You know, if you were to touch any of the pins on the board, you might shock the crap out of yourself. Or the LEDs when it was on. Oh yeah. So this is presumably not so much a transformer as an inductor. So that device there is a 1N60C. That may in fact from Fairchild FE or FQU 1N60C. I thought the 1N series is diode, so that's either an unusual power device or part of the rectification. And the power switching may in fact, well, there's a TO253 part, so that could be the power device. That is I think it's an MDD or something, MDD5N50 C5095 AGG. See, presumably this is output rectification right here. Yep, that's a big diode. So whatever this is, it's got 3 leads, so it could just be like a 2 back-to-back diodes. But it just seems... Can't really see the traces running to it very well. Try and chunk out some of the goo in here. Hopefully without damaging anything too seriously. Oh, there's a big power resistor. There's a number of... just cut myself with a splinter. There's a number of these big, chunky resistors. These are presumably inrush current limiting right here. So interestingly enough, you can see that here's your 2 inlets. You have neutral and hot. Hot runs through a fuse. They both run through big resistors, 2 of them in parallel, in fact. Right across them is this blue component, which is presumably a mauve. Run through that. You go through these 2 big inductors, so that's presumably power factor correction and also noise reduction. I'm actually not too sure how passive power factor correction works off the top of my head. Go through that, and then it goes to... There's this big blob capacitor, which is just across the output of those 2 the inductors. Also, of some interest is there is a 1002, so that's a 10K resistor. There's a little tiny 10K resistor across each of the inductors. Stop focusing on the table, you start. And then it goes through this little tiny service mount bridge rectifier. And then you can see that the output of that is here and here. So, interestingly enough, here's your main capacitor, but it appears there's a diode in series with it. So it runs to the capacitor, but it's kind of hard to understand some of this layout. So in any event, here's the whatever the device that handles the switching is. Let me see if I can get. That is made by NXP, and that is a S3, I think. Hold on. SSL2103, I think. SSL2103. So that's presumably the actual power device, or not the power device, the switching controller. So then there's your transformer, which is presumably like run and flyback or some other topology, because it's not isolated. You can see it's got some stickers on it. Power device under there, presumably for current sensing. Oh, big power transistor, another big power transistor, or potentially a diode, because this is a 1N60. It's a 3-pin package, but it's a 1N60. Well, there you go. So this, just of interest, is this is a 13.5 watt LED controller. It's non-isolated, and here is a this is just a 8 watt controller from another manufacturer. This one, as you can see, there's filter stage is much nicer. It's got a lot more silicon on it. It's got some packs, but the nice thing about this one is the transformer completely isolates. There's a big isolation barrier. So the end result is that for the other LED bulb, you know, effectively this is totally isolated from the line. Whereas on this one, it seems like they didn't isolate it at all. I mean, almost like one of these is, you know, maybe a diode away from line voltage. So the end result is that this one would be a lot safer. So, I mean, I kind of prefer this one just because it's much brighter. I mean, it's twice the wattage. Both of them are fairly nicely manufactured. This one, I mean, it's not terrible. They're all FR4 rather than like shitty, you know, paperboard. I mean, this one uses knockoff capacitors, and this one is actually, these are KY branded. I don't know who made these either, but it does use. The interesting thing about this one is it's non-continuous. It basically, when the line voltage is low, it doesn't do anything. It just relies on the output capacitor to carry it over. In this one, it looks like there's a bridge rectifier and a bulk storage capacitor on the input. So it's kind of a, you know, differing approaches. You know, this one, the whole system starts up and shuts down every cycle, and this one, that just runs continuously, I would imagine. There's a little diode. You know, this one has a lot fewer components. They don't need an opto or anything like that on it. Looks like there's another big diode right down there. So, I mean, on the whole, it's rather interesting. You have two different designs. I mean, this one is non-isolated, but at the same time, the ease with which I pop the plastic off. You know, I mean, the only thing that holds this on is just friction, and no, it's not even friction, it just snaps on. So, I mean, all that prevents somebody from, you know, sticking their finger in the light socket is just that. And yet it's non-isolated, whereas with this one I had to hit it with a hammer to get to the electrical segments, but it's isolated. It seems they're kind of, I mean, it seems like it should go the other way. I mean, they both seem to use the same bulbs, and I mean, honestly, the soldering job on this one is a lot nicer than the soldering job on this one. You can see all the flux there left. But then on the boards, the converse is true. This one has flux goo all over it, and this one has been washed from the look of it. So it's interesting. They're kind of 6 of 1. It's also kind of intriguing how the packaging, you know, basically kind of the style of how they, you know, they pack them is so similar. You know, I guess that the industry has kind of converged on the same thing where they have, you know, the controller inside of, you know, the light socket. You know, I guess that's just kind of, it's standardized itself just by virtue of the fact that everyone does it that way. I kind of like them both. I mean, I have a lot more confidence in this controller because it seems like there's a lot more care gone into it, but I just like this bulb better because it's so much more bright for the same price, so I'll probably wind up buying more of these just because they're cheap. And then just put them in sockets where if they start smoking, I don't care. I mean, one of the nice things is because they're basically in a metal can, I don't worry too much about them burning my house down just because, well, you know, on the other hand, this one, the whole lens is plastic, so I mean, if this thing started venting flame, I can see it making a real mess. Just kind of interesting. There you go. There's another, you know, kind of a competing, much less safe LED bulb design, where they are indeed, you know, the only thing standing between you and line voltage is whatever the dielectric strength of, you know, this is. I wouldn't mind. I mean, I'd like to keep this so I can use it, but it'd be interesting to try and high pot test this. You know, actually, that's interesting. It actually says 18S2P. So presumably this is 18 LEDs, you know, 2 strings of 18. So that also means that they must be relying, the current sharing in here is just based on assuming they're all from the same batch, which is kind of a bad practice. You'd probably want, you know, like a 0.1 ohm resistor in series with each strand just so that you get equal current sharing, because the issue right now is assuming this is a constant current driver. If one of the LEDs in one of the strands burns out, it's going to shove all the current through the other strand and blow that one out in a hurry. You know, so it's kind of poor design. You know, it'll basically means that if any single LED fails, they all fail. You know, if one fails short, you get all the current flowing through that strand, which then blows out more in that strand, which then will cause it to flow through the other one, and then that strand will fail. Whereas if you have, you know, a current sharing resistor of a decent value, you know, if one strand fails, the current sharing resistor will kind of protect it. Though, to be honest, I think no matter what happens, it's kind of, you're stuffed. But anyways, there you go.